Our planet is experiencing a period of significant change, with rising temperatures and shifting weather patterns becoming increasingly noticeable. The scientific community largely agrees that human activities, particularly the burning of fossil fuels, are the primary drivers of this change. This is primarily attributed to the release of greenhouse gases, most notably carbon dioxide, into the atmosphere. The increase in atmospheric CO₂ is often cited as the leading cause of global warming. This is due to CO₂'s ability to trap heat within the Earth's atmosphere, a phenomenon known as the greenhouse effect. While the greenhouse effect is a natural process essential for life on Earth, the enhanced greenhouse effect, caused by human activities, is what raises concern. However, not everyone agrees with this widely accepted view. Some scientists and researchers argue that the role of human activities in climate change is overstated. They point to other factors, such as natural climate variability and the influence of the sun, as potentially more significant drivers of global temperature changes. This brings us to a critical question. What if there are other, more dominant factors influencing atmospheric CO₂ levels? What if the relationship between human activities and climate change is more complex than we currently understand? These questions form the basis of our exploration into the fascinating relationship between sea surface temperature and atmospheric CO₂. The Earth's oceans play a crucial role in regulating our planet's climate. They act as massive carbon sinks, absorbing vast amounts of CO₂ from the atmosphere. The ocean's ability to absorb CO₂ is not static. It fluctuates based on various factors, including water temperature. This is where sea surface temperature enters the equation. SST refers to the temperature of the ocean's surface layer, which interacts directly with the atmosphere. As SST rises, the ocean's capacity to absorb CO₂ decreases. Warmer water holds less dissolved gas, just like a warm soda goes flat faster. This observation has led some researchers to propose an alternative hypothesis. What if SST, not human emissions, is the primary driver of atmospheric CO₂ levels? This challenges the prevailing view that anthropogenic CO₂ emissions are the dominant force behind climate change. To explore this hypothesis, an independent study was conducted to investigate the relationship between SST and atmospheric CO₂ levels. The study aimed to determine whether changes in SST could explain the observed fluctuations in CO₂ concentration over time. This research could potentially reshape our understanding of climate change and its drivers. The study in question sought to analyze the relationship between SST and atmospheric CO₂ levels independently of human influences. The researchers wanted to determine if natural variations in SST could be the primary driver of CO₂ fluctuations. To do this, they collected data on both SST and atmospheric CO₂ spanning several decades. This data came from various sources, including ocean buoys, satellites, and atmospheric monitoring stations. The researchers were careful to use reliable and publicly available data to ensure transparency and allow for independent verification of their findings. The study's core focus was to determine whether changes in SST precede changes in atmospheric CO₂. If a consistent pattern emerged showing that SST fluctuations occurred before corresponding CO₂ changes, it would lend significant weight to the hypothesis that SST is the dominant driver. To analyze this complex relationship, the researchers employed a statistical technique known as multiple regression analysis. This method is commonly used to examine the relationships between multiple independent variables and a single dependent variable. In this case, SST and other potential factors were treated as independent variables, while atmospheric CO₂ served as the dependent variable. The study's methodology involved a meticulous examination of historical data. The researchers first compiled a comprehensive dataset encompassing SST readings from various locations across the globe. They meticulously selected data points to ensure a representative sample of the world's oceans. Next, they obtained atmospheric CO₂ measurements from reputable sources like the Mauna Loa Observatory, renowned for its long-term CO₂ monitoring. By aligning these datasets chronologically, the researchers could compare the timing and magnitude of SST fluctuations with subsequent changes in atmospheric CO₂ levels. To ensure the robustness of their analysis, the researchers employed rigorous statistical methods. They accounted for potential confounding factors, such as volcanic eruptions and El Niño events, which are known to influence both SST and atmospheric CO₂ levels. This involved incorporating data on volcanic eruptions and El Niño indices into their statistical models. By doing so, the researchers could isolate the specific influence of SST on CO₂ levels while controlling for these other natural variables. This meticulous approach aimed to minimize bias and enhance the reliability of their findings. Section 5. Multiple regression analysis, unraveling the complex relationship. Multiple regression analysis is a powerful statistical tool that allows researchers to investigate the relationships between multiple variables simultaneously. In the context of this study, it was crucial to disentangle the potential influence of various factors on atmospheric CO₂ levels. The researchers included sea surface temperature as their primary independent variable, aiming to quantify its impact on CO₂ concentrations. To account for other potential drivers, they incorporated additional variables into their model, such as human CO₂ emissions, volcanic activity, and El Niño Southern Oscillation indices. By including these variables, the researchers could assess the relative contribution of each factor to the observed changes in atmospheric CO₂. The multiple regression analysis would reveal the strength and direction of the relationship between each variable and CO₂ levels, providing valuable insights into the complex interplay of factors influencing Earth's climate system. This approach allowed the researchers to determine whether sea surface temperature had a statistically significant effect on CO₂ levels, even after accounting for the influence of other known drivers. The results of this analysis would ultimately reveal whether sea surface temperature played a more prominent role than previously acknowledged. Section 6. The results are in. SST takes center stage. The study's findings revealed a strong correlation between sea surface temperature and atmospheric CO₂ levels. The multiple regression analysis showed that SST was a statistically significant predictor of CO₂ concentrations, even after accounting for other factors like human emissions and volcanic activity. Surprisingly, the analysis indicated that SST had a stronger influence on CO₂ levels than human activities over the studied period. This finding challenges the prevailing view that anthropogenic CO₂ emissions are the primary driver of rising atmospheric CO₂ concentrations. The researchers observed a consistent pattern. Increases in SST were followed by subsequent increases in atmospheric CO₂. This temporal relationship suggests that warming oceans may be releasing CO₂ into the atmosphere, contradicting the traditional understanding of the ocean as a primarily carbon sink. While the study's findings do not negate the role of human activities in climate change, they highlight the significant influence of natural processes like SST fluctuations on atmospheric CO₂ levels. This underscores the complexity of the Earth's climate system and the need for further research to fully comprehend the interplay of various factors influencing global climate. Section 7. The counterarguments. A look at the other side. The study's findings, while intriguing, have been met with skepticism from some quarters of the scientific community. Critics argue that the study's methodology, while sound, may not fully capture the complexities of the carbon cycle and the multifaceted drivers of atmospheric CO₂ levels. One of the main counterarguments centers around the issue of causation versus correlation. While the study demonstrates a strong correlation between SST and CO₂, critics argue that it does not definitively prove that SST changes are causing CO₂ to rise. They suggest that other factors, such as changes in ocean circulation patterns or biological activity, could be influencing both SST and CO₂ levels simultaneously. Furthermore, critics point to the vast body of evidence supporting the role of human activities in driving climate change. They argue that the study's findings, while interesting, do not invalidate the overwhelming consensus within the scientific community that anthropogenic CO₂ emissions are the primary driver of recent global warming. These counterarguments underscore the importance of ongoing research and debate within the scientific community. While the study's findings challenge conventional wisdom, they should be viewed as a contribution to a broader conversation about the complexities of climate change and the need for continued investigation into all potential drivers. Section 8. Implications for the future. Rethinking our approach. The study's findings, if validated by further research, could have significant implications for our understanding of climate change and our approach to mitigating its effects. If SST is indeed a more dominant driver of atmospheric CO₂ levels than previously thought, it suggests that our current strategies for combating climate change may need to be re-evaluated. Focusing solely on reducing anthropogenic CO₂ emissions may not be sufficient to curb rising global temperatures if natural processes like SST fluctuations play a more significant role. This is not to say that reducing emissions is not important, but rather that it may need to be complemented by strategies that address the natural variability of the climate system. For instance, understanding the factors that influence SST, such as solar radiation and ocean currents, could provide insights into potential methods for mitigating temperature increases. Further research in this area could lead to the development of innovative technologies or strategies for managing SST and its impact on atmospheric CO₂ levels. Ultimately, the study's findings highlight the need for a more nuanced and comprehensive understanding of the Earth's climate system. By embracing a holistic perspective that considers both natural and anthropogenic factors, we can develop more effective and sustainable solutions to address the challenges posed by climate change. Section 9. Conclusion. A call for continued exploration. The study exploring the relationship between sea surface temperature and atmospheric CO₂ levels presents a compelling challenge to conventional thinking about climate change. While the findings do not negate the role of human activities, they underscore the significant influence of natural processes on our planet's climate system. The strong correlation between SST and CO₂ levels, coupled with the temporal relationship suggesting that SST changes precede CO₂ increases, warrants further investigation. It is crucial to conduct additional research to validate these findings and explore the underlying mechanisms driving this relationship. This study serves as a reminder that our understanding of climate change is constantly evolving. It is essential to remain open to new ideas and to embrace a diversity of perspectives within the scientific community. Only through continued exploration and rigorous debate can we hope to fully comprehend the complexities of our planet's climate and develop effective strategies for safeguarding its future.